Welcome to CBSEasy.
Hey everyone, and welcome. Have you ever looked at numbers and kind of felt like there's a secret code hidden inside them? Some kind of logic that makes them all tick? Well, I'm here to tell you there absolutely is. And today, we're going to find the master key that unlocks it all. Let's dive in.
So, that big question, do numbers really have a secret code, a fundamental logic that everything is built on? The answer is a huge, resounding yes. And honestly, it's one of the most elegant and powerful ideas in all of mathematics. And here's the big secret. It turns out that every whole number has its own unique DNA. And this DNA is built from the most basic, indivisible building blocks you can imagine, prime numbers. Seriously, understanding this prime DNA is the key to everything else we're about to get into.
Okay, so let's get to it. This brings us to the master key itself. And it's got a pretty grand name for a very good reason. The fundamental theorem of arithmetic. This right here is the central idea for our whole journey today. Now, when you first read it, it sounds almost too simple, right? It just says that any number that isn't prime can be broken down into a bunch of prime numbers multiplied together. But here's the superpower, the really crucial part. For any number, there is only one set of prime factors that will work. It's totally unique. Okay, theory is great, but let's see this in action with a big number like 32,760. We can just start chipping away at it with the smallest prime, which is 2. We divide by 2, and we can do it again and again, 3 times in total. Then we move on to the next prime, 3, and that goes in twice. We just keep going like this with 5, then 7, then 13, until we can't go any farther. And what are we left with? The unique DNA of 32,760. 3 2s, 2 3s, a 5, a 7, and a 13. So this right here, this is the most important part to remember. You can jumble the order all you want, it doesn't matter. But that specific set of prime factors is fixed. It's a mathematical guarantee. And that guarantee is the foundation for some super useful tools, especially the kind that pop up on exams. Okay, time to get our hands dirty and put this theory to work with our first tool. Using this unique prime DNA, we can find the highest common factor, or HCF, and the lowest common multiple, or LCM, for any numbers you want. This is a total lifesaver when you need to simplify fractions or solve certain kinds of problems on your tests. All right, let's take a classic exam-style problem, finding the HCF and LCM of 96 and 404. And what's step 1? Always, you gotta find that prime DNA. So for 96, it breaks down into 5 2s and a 3. For 404, it's 2 2s and a 101. Okay, so for the HCF, the rule's actually pretty straightforward. First, you look for the prime factors that are common to both numbers. Got them? Good. Now, for each of those common factors, you just grab the one with the smallest power. So let's apply that. What's the only prime factor 96 and 404 have in common? It's 2, right? And what's the smallest power of 2 between them? Well, 96 has 2 to the power of 5, but 404 only has 2 squared. So we take the smaller one, 2 squared, which is 4. And that's it. The HCF is 4. Simple as that. All right, on to the LCM. And you'll see the rule here is kind of the flip side of the HCF. Instead of the smallest power, we want the greatest power. And instead of just the common factors, we have to consider every single prime factor that's involved in either number. So, for our numbers, 96 and 404, we're not just looking at what's common anymore. We need to grab every prime factor we see, 2, 3, and 101. Now we ask, what's the greatest power of each? The biggest power of 2 is 2 to the 5th. The biggest power of 3 is just 3. The biggest power of 101 is just 101. You multiply all of those together and you get your LCM, 9,696. So we've got a killer tool for exams, right? HCF and LCM are sorted, but this theorem, it goes so much deeper. It's so powerful, it can be used to prove some really profound truths about how numbers work, like proving that certain numbers are, well, irrational. So here's our mission should you choose to accept it. We're going to prove that the square root of 2 is irrational. And the way we're going to do it is with this awesome technique called proof by contradiction. Basically, we play detective. We're going to assume the opposite is true and then follow the clues until our assumption leads us to something completely impossible. Ready? Let's break this down. It might seem tricky, but just stick with me. Step 1. We make our big assumption. Let's just pretend the square root of 2 times is rational. That means we can write it as a simple fraction, a over b, that's been reduced all the way down.
Next, we do a little algebra, and we get 2 times b squared equals a squared. Now, what does this tell us? It tells us that a squared has to be an even number. And there's a neat little theorem that says if a squared is even, then a has to be even too. And this is where the whole thing starts to unravel. Because if a is even, we can follow the logic again, and it proves that b also has to be even.
And boom, there it is, the contradiction. Our whole logical argument just fell apart. Think back to the very first thing we said. We assumed our fraction, a over b, was in its simplest form, with no common factors. But we just followed the math and proved that both a and b have to be divisible by 2. They do have a common factor. That's a flat-out contradiction.
And in logic, if an assumption leads you to something that's completely impossible, well, your assumption had to be wrong from the get-go. Our starting idea that the square root of 2 is rational is impossible. So the only thing left that can be true is that the square root of 2 is irrational. And just like that, the case is closed.
Wow. So as we start to wrap this up, just take a second to appreciate how much power is packed into this one single elegant idea. So why does all this matter? What's the big takeaway? Well, first, for your exams, it gives you that rock-solid method for HCF and LCM. No guesswork. But it's so much more than that. It peels back the curtain and shows us the fundamental DNA of all integers. And it's the key that unlocks our ability to prove these deep, profound truths about the universe of numbers. You know, this one theorem shows us that underneath what can look like the total chaos of infinite numbers, there's this incredibly beautiful, predictable, hidden order. It really makes you wonder, doesn't it? What other simple fundamental truths like this are just out there, waiting for us to find them?
Thank you for watching with us. See you next time.